Nuclear physics, science and applications. Perspectives for research in Europe. NuPECC, the Nuclear Physics European Collaboration Committee, which is an expert committee of the European Science Foundation, presents its forward look for supporting nuclear physics in Europe. NuPECC's aim is to strengthen European nuclear science and its applications through collaborative ventures between European research groups. This forward look has involved bringing together the entire nuclear physics community in Europe to formulate how best to develop the field in the coming decade and beyond. It represents the outcome of detailed scrutiny by Europe's leading experts. It will help focus the views of the scientific community on the most promising directions in the field and create a basis for funding agencies to provide adequate support. Europe plays a leading role in nuclear physics research, with more than 6,000 scientists and engineers working at facilities and institutions. At major international facilities such as GSI in Darmstadt, Germany, Guenil in Caen, France, and CERN in Switzerland, researchers can conduct a wide range of experiments. The new FAIR facility to be built in Darmstadt will be a major world centre for nuclear research. European nuclear research also benefits from a network of smaller laboratories which specialise in specific experimental areas while collaborating in developing new instrument concepts and providing training for students. The nuclear physics community through NuPECC proposes to build on current successes in tackling the big questions. For example, how did matter in the universe evolve into what we see today? How is it structured at scales below a million billionth of a meter? And can we exploit what we find out to help humanity solve its energy, health, and environmental problems? Everyday matter is made of atoms with an extremely dense core, the nucleus, which in turn consists of positively charged protons and neutral neutrons. The number of protons defines an element with characteristic chemical and physical properties, and each element can have different numbers of neutrons, giving rise to isotopes. Around 270 isotopes are found on Earth, but thousands more can exist and do exist in the universe, although they are unstable. Protons and neutrons are themselves each composed of three quarks, held together by the strong force, one of four known forces in nature. It's described by a theory called quantum chromodynamics, QCD, whereby fundamental particles called gluons mediate the strong interaction between the quarks. Nuclear theory is immensely complicated because many particles are involved and gluons also interact with themselves. Experiments probing nuclei and their constituents require large-scale equipment, machines to accelerate particle beams to reasonably high energies before being collided with a target or another particle beam to produce new particles that are identified and characterized. Of increasing importance are facilities generating the ion beams of unstable or radioactive isotopes and antimatter particles such as antiprotons and positrons. Advances in infrastructure and instruments crucially depend on innovative technologies, so that research groups often collaborate to develop central facilities to be used by large numbers of scientists for a variety of experiments. QCD studies, which encompasses a hierarchy of complex theoretical approaches, also require central supercomputing facilities to model the interactions of nuclear particles. One of the most intriguing questions in science is what is the origin of the 92 natural elements that make up our world and us? We know that most of them are made via nuclear reactions in stars. The nuclear landscape shows the complex reaction paths occurring during the life of a star, which nuclear physicists try to untangle. Stars build up the lightest elements by burning hydrogen to helium via two reaction cycles, the PP cycle and the CNO cycle, followed by further element building processes. Eventually, the heavier elements up to iron and beyond are created, although at a very slow rate. The heaviest elements are created as a star dies. Very massive stars end their lives spectacularly in a supernova explosion, in which cascades of ultra-rapid reactions are thought to generate elements up to uranium. Such studies tell us much about the evolution of the universe and about stars like our Sun, whose energy output affects our climate. They give us a better idea of planetary development and how the element abundances necessary for life came about. Nuclear astrophysics is challenging to study. For example, underground facilities protected from interfering radiation are required to measure rare reactions, and beams of unstable isotopes to probe rapid nuclear synthesis in supernova explosions. Thousands of species of atomic nuclei with different ratios and numbers of protons and neutrons can exist. So far, only about 1/4 have been studied. They can be mapped out on a landscape accordingly. It features a diagonal valley of stability marked in black where the familiar stable elements live. The bordering yellow regions harbour known unstable species, and in the grey area, exotic unknown nuclei with extreme ratios of neutrons to protons survive transiently. At the top right is a mysterious island of stability of unknown super-heavy elements. The stability of a nucleus depends on the numbers and proportions of protons and neutrons, which are arranged in shells. Nuclei with fully filled outer shells are especially stable, and are characterized by so-called magic numbers of protons and neutrons. In the more extreme regions of the nuclear landscape, nuclei may have unusual shapes and new shell configurations having different magic numbers. Studying nuclear structure and stability requires creating exotic nuclei. This is achieved by breaking up or fusing nuclei when accelerated particles hit a target. The lifetimes, masses, and decay properties are then measured. The information not only throws light on our fundamental understanding of matter, but is also relevant to applications using radioactive isotopes. There is still much to find out about the factors affecting nuclear structure and behavior, which require the generation of intense beams of both stable and radioactive ions. Protons and neutrons belong to a class of particles, all composed of quarks and gluons, called hadrons. Because quarks and gluons are never seen in isolation, hadrons represent the first observable level of complexity in matter. Hadron physics aims to study how this complexity is generated through the action of the strong force. Quarks combine in pairs called mesons, and in threes known as baryons, and in even more complex structures. They include short-lived hadrons containing types of quark not found in everyday matter. Protons and neutrons consist of the two lightest quarks known, called up and down, but 4 other quarks exist called strange, charm, bottom and top. Various exotic quark-gluon combinations are predicted but not yet observed. Gluons are even thought to self-interact to form glue balls. Even the structure of the humble proton remains a puzzle. The spin of the proton should be made up of the spins of its constituent quarks, but they account for only a third of the spin. To study such phenomena, dedicated accelerators generating high-quality beams are needed, such as PANDA at FAIR, and also continual support of the accompanying theoretical work, which requires high-performance computing. Europe has led the way in hadron science thanks to existing smaller facilities that provide expertise and specialist input.